Okay, let's take a look at this hypothesis test. You wish to test the following claim. H sub alpha, or our alternate hypothesis, at a significance level of alpha equal to 0.005. And our null is that our mean is 80.5, and our alternate is that the mean is less than 80.5. All right, now, since it's less than, think of this as pointing toward the left. Our critical region is to the left. So if I draw the normal curve, it will, I apologize, my drawing's not great on the computer, but our critical region will be here on the left. And in a minute, we'll mark our critical value right here where I've got this line. Okay, so let's find our critical value first, though. So we have that alpha is 0.005, and since it's a left-tailed test, all we have to do is look up 0.005. Now, I'm going to use Excel for this, and to do that, I'll just open Excel. I can go to any cell in Excel that I want, it doesn't matter, and go equal norm.s.inv, oops, and I'm going to put in 0.005. And that gives me a critical value of negative 2.576, since we wanted to go to 3 decimal places. So negative 2.576. Now, I won't enter that in here because this is actually your homework, but I will put it in this picture. Kind of hard to draw with your mouse, but you get the idea there. So that right there is the negative 2.576. So if we get a number that is to the left, negative 2.576 on the number line here, it will be in this critical region. If we get something to the right, it will not be in the critical region. So let's go ahead and look at doing our test statistic. And you notice that I've got the answer showing here, so we can see, yes, that was the critical value. Now, let's get our test statistic. We need to plug it in, and I didn't open a Word document. Do that real quick. And we're going to do our z-score, but it's the newer z-score with the square root of our sample size in it. All right. So we're going to have z equals our x, in this case, our x bar, if we look back, is 69.7. And then our mean is 80.5. Our standard deviation is 16.7. And we have a sample size of 20. So if we plug those values in, we'll have our sample mean first, followed by our population mean, divided by our standard deviation, divided by the square root 20. All right, so if I work this out, on top, 69.7 minus 80.5 ends up being negative 10.8. Oops. And then on the bottom, 16.7 divided by the square root of 20 ends up being this decimal. Now be careful, don't round off too early when you're doing that bottom calculation, or you may get your z value off. So take it out 6 or 7 decimal places. All right, now if I divide those two out, negative 10.8 divided by the 3.734234, I get 2.892. Now let's notice negative 2.892. Go back to my drawn picture. That is to the left of negative 2.5. So negative 2.8 is a little bit over here, which puts it in the rejection region. So when we go back here, negative 2.892 was our test statistic. It is in the critical region. And when something is in the critical region, we reject the null hypothesis. So we would have reject the null hypothesis. Now, whenever we reject the null hypothesis, there's always evidence to support our alternate hypothesis. So we always want to say there is evidence to support that alternate. So let's take a look down here and find something that says there's evidence to support our alternate, and our alternate is that the mean is less than 80.5. So let's see. There is sufficient evidence to warrant rejection of the claim that the no, we don't want to reject the alternate. There is not sufficient evidence. No, we know there's evidence. So the sample data support the claim that the population mean is less than 80.5. There it is. It's supporting the claim, the alternate, that the mean is less than 80.5. So it would be this one here. Okay? So, now, the rest of them you're going to do in a similar fashion, but if our alternate is not equal to, when we start our process for the critical value, we have to divide this by 2 because there's a two-tailed picture. In other words, let me see if I can do another. So for that two-tailed test, it's going to look like this, where we have a tail out here that is a rejection region and a tail out here on the right that's a rejection region. So the only thing that's different is finding the critical value. And when we find the critical value, we will take the 0.001 in this case and divide it by 2. If we divide that by 2, we get 0.0005. And if we put 0.0005 in here, equal norm S INV 0.0005, we get a critical value of negative 3.291. Now, what that means is negative 3.291. That's the critical value on the left. And there's also a critical value over here. And it's the same thing, it's just opposite side. So when we do the test statistic, which we will do in the same way we did the previous example, if our test statistic falls to the left, negative 3.291, or to the right, positive 3.291, it will be in the critical region. So that's our two-tailed test. Now, our right-tailed test, and I'm not going to do all the steps of this because it will be exactly the same idea as the last one. It's just the only thing difference is that critical value. And let's see if we've got a right-tailed test. And that's left-tailed. There's a right-tailed one right there. All right, so again, the only difference is going to be in finding your critical value. So if we draw the picture for this one, the critical region will be to the right. But what you've got to do to begin with is subtract alpha from 1 if it's a right-tailed test. So we're going to say 1 minus 0.05, which is 0.95. And that is what we stick in here. And we get that our critical value is 1.645. And so anything to the right of 1.645 would end up being in the rejection region. So notice, if it's to the left, you just put it into Excel and get the value. If it is a two-tailed test and not equal to for your alternate, you're going to divide it by 2 and put it into Excel. And if it's a right-tailed test, you're going to subtract it from 1 and then put it into Excel. Hopefully that will help clarify.